Alright, so this video is going to show how we get the motion for a mass on a spring from the motion of a mass around a circle that is undergoing uniform circular motion. So I have the system that is the mass on a spring drawn here on the right. That's what we're looking for the motion of. And I have a mass that's traveling around a circle uniformly. That's what we're going to use to find the motion of the mass on the spring. And we're going to do this by constructing the square of similarity. Essentially what we're going to do is use what we know about uniform circular motion to get the x component of the mass's position, velocity, and acceleration, and then show that those have to be similar to, or will be the same, as the acceleration, velocity, and position of the mass on a spring. So let's do that. Alright, so first let's look at the uniform circular motion. I want to write down what the x-coordinate of the mass's position is as a function of time. So this little point right here has an x and a y position. The x-coordinate is what I'm interested in here, and I want to write that down as a function of time. So if I look at the triangle that includes this angle, then this distance here is the x-coordinate, assuming that we have the origin at the center of the circle. So remember, from uniform circular motion, we know that this angle, as the mass travels around the circle, that angle is going to increase, and it's going to increase with some angular velocity, and we call that angular velocity omega. So that means that the x-coordinate as a function of time can be written as the radius of the circle times cosine of the angle, which means that it's cosine of omega t. Now, to get the velocity as a function of time, I just take the derivative of that. So the derivative of cosine is going to give me a negative sign, and there's also an omega that's going to come out. So I'm going to write the omega here. There's a sine omega t, and put a negative sign there. And then the acceleration as a function of time is going to be the derivative of the velocity. Let me get rid of this arrow real quick. So derivative of the velocity is going to give me negative r. Another omega is going to come out, so I've got omega squared, and I've got cosine omega t. Now, if I look at r and cosine together, that's actually just x, right? So I could rewrite this as negative omega squared x. That's what the x component of the acceleration on this mass that is traveling around a circle is going to be. So let me write that as the x components. Now this is very similar to the acceleration of a mass on a spring. Recall that the mass on a spring is going to experience a force. F is equal to ma, and the force is given by Hooke's law. So that's negative kx. All right, so the acceleration is negative kx over the mass. So I can draw a similarity, or I can draw the bottom part of my square here and say that, well, if omega squared is k over m, then these accelerations look the exact same. One thing I will point out is that I have got the maximum amplitude of the mass's displacement written as a capital A, and if we look over here, the maximum value for the x component of the position for the mass going around the circle is going to be r. So I also am using slightly different notation here. So I just make the comment that r is equal to a. When I go from the circular motion over to the mass on a spring, omega squared is equal to k over m, and r is equal to a. All right, so it's the acceleration similarity that allows us to make this connection. So now I just start going up the ladder. Right, so if this is the acceleration as a function of time for the mass on a spring, then I can write down the velocity as a function of time. Again, omega is going to have to be the square root of k over m if omega squared is equal to k over m. And I can write down the position as a function of time. So there we have it. That gives me the motion for the mass on the spring. I started with the motion of a mass around a circle. I wrote down the position, well, the x-coordinate of the position as a function of time. Took the derivative to get the x component of the velocity as a function of time. Took the derivative to get the x component of the acceleration as a function of time. I noticed that the acceleration is basically just something that looks like Hooke's law. It's got a negative sign, some constant, and then the x-coordinate of the position. So if I make this connection that omega squared is equal to the spring constant over the mass, I can see that the acceleration that the mass experiences on a spring is very similar, which means that I can use the velocity of the uniform circular motion to determine what the velocity of the mass is, and I can use the position of the uniform circular motion to determine what the position is. And now I have completed my square of similarity.